In this second presentation on linear systems, we will introduce two important concepts. First of all, the concept of complex quantities, which turns out to be very useful when we deal with linear systems. And secondly, the concept of frequency response function, that is, as should be shown later on, used to describe the path between an excitation and the response. And we will use an example, a simple example, to show, to illustrate these concepts. So let us consider now a simple mechanical mass spring system. The mass is m, and the spring constant is kappa. And let the mass m be excited with a sinusoidal force with amplitude f hat and frequency f. So 2 pi f here is the angular frequency. And let us denote then the mass degree of freedom with x. So this system's response, that is x here, is governed by the equation of motion, which is the inertia forces, mass times the acceleration, which equals then the excitation force, F, minus the spring force, which opposes the motion. And that is FFE here. So, using the characteristic equation then of ideal mechanical spring, we obtain this relationship where kappa times the displacement x here is the spring force, the stiffness force. So if we rearrange this equation, the equation of motion, we get this differential equation. So how to solve this? Well, since it's a linear system, we know that it must be frequency conserving. That is, the displacement, the responding displacement must be possible to write in this way. We have two components, a sinusoidal and cosine component, which have the same frequency as the excitation. If we then we have unknown constants, A and B. If we combine these now with trigonometric formulas, we can write it in this way, where x hat, is the amplitude of the displacement, and the phase angle phi here describes a phase shift with respect to the exciting force. So this we know because the system is linear. So we now have to determine the x with respect to f here and the phase angle. And to do this, we insert this equation in the equation of motion, identify terms, and then use some algebra. And we then will find the response after some quite tedious calculations. Even this simple example takes some time. In order to simplify the algebra, we can use something called complex quantities. And what we do then is that we change the trigonometric time dependence to a complex exponential corresponding time dependence. So in this case, we have sine. So we change the sine we saw earlier here, the sine term, to the corresponding complex exponential. So you see here, sine has been changed with e, the exponential raised to I times the 2 pi ft. And this, if we introduce instead the angular frequency omega, the complex force reads F times e raised to I omega t. And if you do the same now with the displacement, we obtain a complex displacement. In the same way, we have now a complex amplitude, and this e I 2 pi f term, the complex exponential term. And once again, if we introduce the angular frequency, it reads x times e raised to I omega t. And it turns out then that the complex amplitude contains both the magnitude, well, the magnitude of the complex amplitude is the size of the displacement amplitude, and the angular part of it contains the phase shift relative to the excitation. To determine the complex amplitude now, we introduce this into the differential equation like this, and we perform the time derivations and obtain this. And then we simply solve for x and get this expression. And now we can identify the system's frequency response function, h, which is what we have to multiply the exciting force with to get the responding displacement. So this expression here, this factor, is what we know as the system's frequency response function. And as you can see, it depends on the system properties, that is spring constant and mass, and the excitation frequency, omega. So, to conclude, linear system models, they are very powerful tools to analyze a system's response to an excitation. This we will see later on, but we can already now conclude this. Secondly, a linear system's frequency response function depends only on the excitation frequency and the system properties. So it does not depend on the excitation, not at all. And finally, the calculations are simplified if we use complex quantities.